Number 17 is a slightly different type of probability problem where we're dealing with, you have to come up with the probabilities first. That's the first thing we're going to do, and that's what we're going to do right now. So you've got the junk box that everybody owns, and you have a dozen batteries, 5 of which are totally dead. So let's come up with some probabilities first. So our first probability is that we get a good battery, right? And that's going to be 5 are dead, so 7 are good. 7/12 probability of good, and the probability of bad is 5/12. 5 are totally bad. So now we're looking for the probability of each outcome described below. So part A, we're finding the first 2 you choose are good. We're looking for the probability of a good and a good. Now we have to ask ourselves, are these independent events? It's a multiplication rule because we're writing it as and. A good one and then another good one. But we just have to check, are these independent or are they not independent? Since we're pulling one out and not putting it back in, we need to, so why would we put it back in? These are not independent, meaning these are going to change as they happen. The first event, the probability that we get a good one on the first one is 7/12. Usually that one is pretty normal, if you will. And then holding the good one in our hand, we're reaching in for a second one, but we've got one in our hand. Not only do we have one battery in our hand, we've got one good battery in our hand, meaning that numerator is going to go down, as is the numerator, the denominator rather. I don't know what I was going to do there, but so as we're looking at that math, right? I don't happen to have that one done, but we straight up, it's just a multiplication problem of so 42 divided by what, 132. And we've got 0.3182 is our probability. 3182. At least one of the first 3 works. Okay. Anytime we see at least one, that is the complement of none. Because if we're picking 3 batteries and we want at least one to work, that means we have to find the probability of all of them working, to find all probabilities of having 2 of them work, and having all the probabilities of having one of them work, and add them all together. Well, that's a lot of work. So let's do it. The probability of at least one is the probability of none. There's a complement, rather, of none. So I'm going to try to leave myself some room here. I hope I don't run out of space. And we're looking at 1 minus, right, the probability of, I'll just put it in parentheses here, of 3 bad. I'm going to clean that up. That's bothering me. That's bugging me. One minus. So the probability that we get a bad one on the first is 5/12 times 4/11 times 3/10. You're going to want all that in parentheses. You can do it all in the calculator. It will take some pretty heavy parenthesis use to do that. You'll want parentheses around everything within the parentheses. So that might lead to, if you get some sort of a formatting error on your calculator, you might have just forgot to close a parenthesis. So it is just something to be aware of as you go. But you have a pretty good chance of getting at least one that works if you pull 3. And on to part C. And I'm going to thin this line out again here. The first 4 you pick all work. Good and good and good and good. All right. And if they were independent events, that would be awesome. We could make use of the exponent function on our calculator, but we can't because they're not independent events. And we started it up above. I guess if you wanted to just take that answer and keep going with it, you could. But it's easy enough to write these out. 5 over 10 and 4 over 9. Just double checking there. It's not all that likely. I think that actually works out to that exactly. I don't think, or 7-1, 7-1, I'm sorry. 7-1. Can't read my own writing. And then you have 5 batteries. You have to pick 5 batteries to find one that works. This might seem like a different type of question that we haven't really been asked, but just put it in the context of what you're doing. What it's really saying is, what's the probability that the first good one you find is the 5th one you select? So in terms of what it looks like, a bad, a bad, a bad, a bad, and then a good. Right? So I don't think I need that anymore. So 5/12 times 4/11. The second one is bad. The third one is bad, is 3/10. The fourth one is bad as well. 2/9. Now we're at the good one. We've selected nothing but bad ones, so there's 7 good ones left. And it's only 8 left. But the likelihood that this is going to happen, that we're going to have to wait to the 5th one to find a good one, is pretty unlikely. Pretty unlikely if we do that math out. It gets to be about 0.09. Okay? Not all multiplication rule questions are going to have and. Not all addition rule problems are going to have or. You have to be ready to rephrase them as such so you can know, oh, this is multiplication or addition. You also have to recognize when things are independent and when they're not, and how does that affect the probabilities you're using. Again, let me know if you have any questions. I hope this helped.